Hi everybody, welcome back. So note down the heading, Electroneutrality Principle. Electroneutrality Principle. Okay, so we said yesterday that if you have a metal, there are ligands who are ready to donate their lone pair of electrons to the metal. And where does it enter to? It enters into the vacant d orbitals of the metal. Right. Now you consider a octahedral complex, for example. Now when you consider an octahedral complex, you have one ligand, two, three, four, five, and six. Correct? So any octahedral ligand that you take will have six ligands. All of these ligands are giving its lone pair of electrons to the metal. That means the electron density at the metal is increasing. Correct? Let's say that this is giving one lone pair of electron. So one lone pair of electron gained from first ligand. This is from the second ligand. This is from the third ligand. This is from the fourth ligand. Fifth and sixth. So you can see that there are six ligands that are surrounding the metal, all of them providing one lone pair of electron each, and that would accumulate the negative charge on the metal. Okay, that would accumulate the negative charge on the metal. So, electron neutrality principle predicts predicts the thermodynamic stability. Predicts the thermodynamic stability of non-transition metal complexes. Non-transition metal complexes mostly. So pay attention, non-transition metal complexes. Mostly, okay. You can use some complexes and compare the stability using electroneutrality principle as well. But mostly non-transition metal, because for transition metals, you have a lot of other theories. Valence bond theory, crystal field theory, ligand field theory. There are many. Okay, so for non-transition metal complexes, to predict the stability, you have got some principle which is called electroneutrality principle. According to the electroneutrality principle, the charge around the metal should not be accumulated in such a way that it loses the stability. Okay, so there are many ways by which the electroneutrality principle can be explained. So I'll explain one by one with possible examples. Okay, so let me try. So the first one is, first point, note it down. First point is the electronegative ligands stabilize the formal charge. So you should know what formal charge is. We'll do that. So it says that electronegative ligands stabilize the formal charge. Understand that formal charge and stability are inversely proportional. Formal charge and stability are inversely proportional. So how do you find the formal charge? Okay, so let's do an example corresponding to this electronegative ligands and how do they stabilize. So you note down a question. This was asked in one of the exams, BARC. Okay, so you have to compare the thermodynamic stability of aluminium H2O 6 times 3 plus, aluminium NH3 6 times 3 plus, and aluminium F6 3 minus. 3 plus, sorry, 3 plus. Okay, so you have been given three non-transition metal complexes with different ligands. So you have to know which one among these is the stable. You can understand that in all the cases, there is a lone pair of electrons being provided to the aluminium. And hence, aluminium gets accumulated with a lot of negative charge. So we don't want that, correct? We want a balance. Neutrality is what we want. So with respect to that, which one is stable is the question. So first of all, we have to find the formal charge. How to find the formal charge? So to find the formal charge, each ligand gives one pair of electron and one pair of electron would be given a charge of -1. Okay? Note, one lone pair is equal to -1 charge. Okay, so what is the oxidation state of aluminium here? Water is a neutral ligand. Aluminium, let's say, is X. This is 6 into 0, gives you a total charge of 3. So aluminium over here is +3. Correct. Similarly, ammonia is also a neutral ligand. So of course, the same. This is going to be X. This is going to be 6 into 0. And the total charge is 3. So this is X is equal to +3. Here, fluoride. We said that fluorine, chlorine, bromine, those are never going to be a ligand because its octet is not complete. So it should be fluoride. So if it is fluoride, this is -1 into 6, giving 3. That is X minus 6 is equal to 3, X is equal to +3. So we can see that the oxidation states of the metal are same throughout. Correct. They are the same throughout. Then we have to find the formal charge. How to find the formal charge? Listen, oxidation state of the metal is 3. Water gives 6 lone pairs of electron. One lone pair of electron carries a charge of -1. So 3 minus 6 is equal to -3. Here also 3. Ammonia also gives only one lone pair of electron. That is -1 for each ligand. There are 6 ligands. So that is also equal to 3. -3. Here also, fluoride gives one pair of electrons. So 3 minus 6 is equal to -3. So the formal charge is the same. So based on formal charge, we cannot differentiate them. Okay, we cannot differentiate them. So we said that as formal charge increases, stability decreases, but the formal charges are the same. So the next parameter that you can check is the electronegativity of the ligand. See, here it is water. Here it is ammonia. And here it is fluoride. Correct. So among all these, we know that fluorine is the most electronegative atom. That means the extent of donation, even though whatever happens, if this is donating to the metal like this, the 2 electrons would be shifted towards the fluorine because it is highly electronegative, correct? So the electronegativity of fluorine is larger than oxygen and larger than nitrogen. Correct. Isn't that so? So as a result of which, what happens? Here, the negative charge does not accumulate much on aluminium because a little bit of density is pulled towards fluoride. So there is no much accumulation, and as a result, the order of stability is aluminium F6 3 minus is the most stable. Then comes aluminium H2O 6 times 3 plus, and aluminium NH3 6 times 3 plus. This is the order of stability. This is the order of stability. Okay, this is one aspect of the ligand. Ligands can have different electronegativities as a result of which stability changes. Second point is electrons, not electrons, ligands, sorry. Ligands with vacant pi star orbitals stabilize the formal charge. You will be learning about this deeper with all the diagrams and all. But just understand that for ligands like carbonyl, nitrosyl, NO, just NO. Okay. These ligands have pi star orbitals that are vacant. So if there are pi orbitals, there would be pi star orbitals as well. And these species have got vacant pi star orbitals. So what do? If these ligands are attached to the metal, so initially carbonyl will give a lone pair of electrons to the metal, and then metal will donate back the electrons to the pi star vacant orbitals of carbonyl. So in such a manner, accumulation of charges won't happen at the metal. I hope you're getting the point. Okay. So when you have ligands with a vacant pi star orbital, after the donation of a lone pair of electrons to the metal, there is a back donation of the electrons from the metal to the vacant pi star. As a result, accumulation of charges won't be there at the metal, correct? And this would stabilize the formal charge. Second point. This is the second point. Third point. So these are with respect to the ligands. These are with respect to the ligand. See, property of a ligand. This is also a property of the ligands. Now, next one is with respect to the metal. Metals with higher oxidation states are more stable. Metals with higher oxidation states are thermodynamically more stable. Why? Let's see an example. Let's say you have NaH2O 6 times plus MgH2O 6 times 2 plus AlH2O 6 times 3 plus. So in all these cases, you can see that the ligand which is attached is just water. Okay, and first of all, you find the oxidation states of the metal. So water is a neutral ligand. So the oxidation state of sodium over here is +1, +2 for magnesium, and +3 for aluminium. Now to find the formal charge, we know each ligand, if it donates one lone pair of electrons, then it will contribute a charge of -1 towards formal charge. So here 6 ligands, -6, -5. 6 ligands, -6, -4. Here 6 ligands, -6, -3. So can you see? The formal charge changes with the oxidation of the metal. So here -5 units of charge is accumulated on the sodium, and that is least stable. While here there is only -3 of negative charge which is accumulated on aluminium, and hence that is the most stable. So this is a trend. Sodium complex is least stable, followed by magnesium and aluminium with the most thermodynamic stability. Okay. So this is with respect to the metal. Okay, one more with respect to the metal. Metals bonded with lesser number of ligands. Obviously. That is obvious. That is, let's say you have NiCl6, 4 minus, and you have NiCl4, 2 minus. So if you can see here, there are 6 ligands. Here, there are only 4 ligands. Correct. So what happens over here? What is the formal charge? Please find the formal charge. The oxidation state of nickel over here is +2. Here also it is +2. So the formal charge is 2 minus 6 is equal to -4. Here it is 2 minus 4 is equal to -2. See, the accumulation of the charges on the nickel is less when the number of ligands are less. That is obvious. We do not even need to do this calculation. If there are only 4 ligands, only that much of electrons will come and accumulate on the nickel. While here there are 6 chlorides and it will accumulate after the donation, the electrons would accumulate at the nickel. Correct. So this is more stable. It's not about stability. This does not even exist. Does not exist. It's not at all stable. It is not at all stable. Okay. So similarly, there are other species like Ni chlorine. Then who's the next? Bromine, Br6. They do not exist. NiI6 4 minus. They don't exist. Okay. Why? Because it leads to a lot of accumulation of the charges on the nickel. Okay, so that does not exist. So I hope you get that point. But if you can see NiF6 4 minus does exist. Can you tell me why? We said that chloride, bromide, and iodide based this nickel complex does not exist, but fluoride based nickel complex exists. Why? That is because fluorine is very electronegative. It does not accumulate the charge on the nickel to the extent as chloride, bromide, or iodide. Okay, so NiF6 4 minus is there, but the others are not there. So these are all simply explained based on the electroneutrality principle. So we have discussed 4 parameters, 2 with respect to the metals and 2 with respect to the ligands. Very easy. 2 to 3 times questions have been asked. Okay. Now one final thing that, see, understand that if you have a complex with same oxidation state, you have got a complex with same oxidation state and different configuration. D0, D1, D2, D3 will write up to D10. Okay. If so, understand that up to D5, the electrons which are present on the metals are relatively low. The extent of negative charge due to the electrons present in the metals are relatively low. As a result, their coordination number is higher. They can accommodate more charge. So you know what coordination number is, right? Coordination number is the number of donor atoms. High coordination number. Because they have a lot of space to accommodate more charge. While if you take D7, D8, D9 and D10, they are already full. They are already full. So they prefer low coordination. They prefer low coordination. Okay. So that's it. Now you might think, what about D6? It is variable. It cannot be predicted. It's variable. All right. So with this, we come to an end of a very easy peasy session. See you in the next.